All right. Look, I'm a little frustrated, and I think deservedly so. Your three columns gave you kind of a place to start. Force problems are really good at finding a force or an acceleration. Not particularly good at velocities because you have to use something else afterwards. But once you have an acceleration, you can generally find a velocity or a change in velocity. Energy problems do a really good job with displacements and velocities. That's really how they shine. We look for things to see if energy will probably work. One of the things we look for is a change in height of the center of mass. Momentum problems often deal with collisions. And I don't think momentum really applies here. I don't see a collision. Do you see a collision? I do see a change in height. So there's every reason to believe that energy would work here. The problem is that every time we've done an energy problem, it hasn't figured out an acceleration, right? The change in height generally was something that we used to find out how fast something was going. That doesn't mean you can't use it here. Again, these were suggestions. You have to find a starting point. So even if you pick wrong, pick something and go with it. No matter what, you're going to have to create things in service to the problem. That's what you guys tend to miss. But you need to service the problem. For example, if I'm going to use energy, and I'm not saying that that's the right method to go, but the height of this object clearly changes over time, doesn't it? And because of that, it will eventually be at a lower position. Now, I don't know what this height is because it's a variable that was not given. I am creating a variable in service to this problem. In the end of the day, h can't be in my answer, but I can use it now in service to my problem. So I'm going to serve this problem. I'm going to try and work out this problem using energy. Even though I presented it in class, and you should know that when we presented it in class, we use forces. But I'm just, again, I saw a change in height that triggers one of our things. So I'm going to make this the lowest point of the problem, and I'm going to say that it has all, what kind of energy up here at the top? All right, so all mgh here at the top. It is not moving. It's being released from rest. So I'm going to put off to the side here. Its initial velocity is 0. If this represents the lowest point in the problem, what kind of energy are we likely to have when it unrolls to that point? What kind of kinetic? We know there's more than one now. Is it going to be moving downwards? Like, is the center of mass moving? If it is, then it has translational kinetic. Is it spinning? Then it has rotational kinetic. And yes, this is not weird stuff. I'm going to stop right now. We're assuming this is a conservation problem. So I think the energy we have here will be equal to this energy here. So that's what I'm going to do next. I'm going to set them equal to each other. So this equals 1/2 mv squared plus 1/2 I omega squared. Now, I'm looking for acceleration. I'm going to point out that I don't see A anywhere in here yet. But I'm serving a different problem. I'm thinking of the future of this problem when I'm probably going to know what, say, delta x is, right? We set that. We said that delta x is h. And I know that I have an initial velocity of 0, but I'm going to have a final velocity. I could probably get something for the final velocity later. I'm seeing the pieces laid for a motion equation, right? I'm seeing the pieces there. So I'm thinking, although energy won't give me acceleration, energy might give me enough stuff where I can use a motion equation to get acceleration. So I know that energy is good about giving me velocity. So I'm trying to put together a roadmap, and I'm hoping in the end, H cancels out. Well, and M and R and all the other stuff. I'm hoping. I don't know. I've got to work the problem out. So I'm using the rules that I've established. And the first rule here that I've used is conservation of energy. And that gave me a relationship to start with. I'd like to reduce the number of different things I have here. And so there are things I can introduce to help reduce that. For example, is its rotational speed linked to its linear speed? Are these things linked up? Is it unrolling? If they are linked together, then I can say that V equals omega times R. That's an if, but for something like this, you should always ask it. It's going to reduce the number of variables. It's going to take away omega and put something in terms of R and V. And since this already has V in it, it's nice to have everything in terms of the same V. So that's where I'm going to go. I'm going to make that substitution. Now, obviously, I left some parentheses there because I know what I is. I has something to do with the shape of the object. What shape are we using here? A disk. So I'm going to use the moment of inertia of a disk. Again, in service to the problem, a disk. Yeah?
Would it not be a thick ring?
We could use thick ring too. So I'm not doing a thick ring in this example because I'm using the example that we used at the very beginning. But you're right, and I asked that question. So you should probably take a look in your lab and see how would a thick ring change this. I know what I think the answer should be, but I'll let you kind of work that out. I'm noticing that I can do some algebra here. And so I tend to gloss over the algebra as much as I can because I think it's the least interesting thing. But if there's algebra you're missing, you should probably speak up. We did this exact algebra yesterday, though, so I don't feel so bad about it. The thing rolling up the ramp. And so I get mgh equals 3/4 mv squared. First, I'm noticing something good. The m's cancel. I got rid of one of the variables, and that's great. And so I can write v squared as 4/3 gh. I'm getting close. If I have h in my answer, that's not going to be great. But I could take the square root, and now I have the velocity. This is the final velocity after it's fallen a distance h. The final velocity after it's fallen a distance h. It's not the answer, but we haven't gotten to the answer yet. The answer is about acceleration. Energy tells us velocity. So now I need to bring in something else if I want to find acceleration. But I'm going to stop here because some of you won't persevere this far. You have to understand the limits of what a particular topic has. And one of the limits in energy is that it's path independent, which means it doesn't care what the pathway that you took is. And the next limit is that it doesn't really work. It doesn't tell you acceleration. In fact, it works in situations where you don't know the acceleration or don't have it. It even works in situations where the acceleration isn't constant. You have to ask an important question here before you can go on. And that is, does the object have a constant acceleration? That's the only way you can use a motion equation, is if the acceleration stays the same all the time. You have to make that decision about whether it does. If it doesn't stay the same, you can't use a motion equation. So, what do you think? Do you think the acceleration is a constant as it unrolls? There's reasons to believe it probably would be. For example, as it unrolls, is the path a straight line? That's a good example of probably why it is. The other one is probably that the fact that the forces acting on it are always the same. They're never in a different direction or anything like that. But it's a question you have to ask yourself. Now, I think that there's a motion equation that has these four things in it. Do you? Can you tell me what it is? What's that?
2a delta x equal v squared.
That's it. All right. We want A. So 2a delta x is h equals v squared 4/3 gh plus 0. All right. Get rid of that 0. And I'm noticing that both terms have an h in them. So 2a equals 4/3 g. Can I just divide both sides by 2? Now, this is not how we did it in class, but it worked just fine. I will point out, I hoped that the variables I created for this problem would work out in the end. I created variables for this problem, right? I didn't have an h, didn't tell me how far it fell. I actually created other variables. I mean, this v and this omega. These are variables that I had to create for this problem because I had nothing to do. They weren't given to me, but I created them in service to this problem. Now, this is not the way we did it the first time. If you look back at the way we did it the first time, we used forces as our method. In fact, I would prefer it be about forces because that's what we were studying at the time. But we're studying energy now. And all of these rules have to work together. I always make the joke that this isn't chemistry. It's not filled with exceptions. Chemistry always felt like it's filled with exceptions to me. You know, everything works this way until you talk about this other substance that works that way. Right? Everything gets smaller as it gets colder, except water, the most prevalent thing on the planet, expands when it freezes. But everything else gets smaller when it gets colder. That's a big exception, isn't it? I like rules. These rules have no exceptions. They always work the same way every time. You have to apply them correctly. Now, I want to be very clear. You should be able to do the force problem. And I want to show you something about the force problem on purpose. This was a great start, but if you did the force problem, which is what the other side of the room was doing, you had to do different things in service to this problem. You had to create variables, and those variables may or may not have been allowed in your answer. For example, one of the variables you probably created were the two forces acting on the object. So did you create a force to describe the weight of the object? It's a good idea to do so. Did you also create tension to describe the upward force provided by the toilet paper? If you did, you created variables in service to this problem, variables that can't be in the answer. Right? M can't be in the answer, and T can't be in the answer. We have created things in service to this problem that can't be in the answer. It's always going to happen. If you're using energy as your argument, the next thing you probably would have asked yourself, net force equals 0 or ma? We know it accelerates, and we know it spins. So in service to this problem, we are applying a set of rules. Now, look, your columns. I put them in columns for you because I wanted you to have a new place in your notes, problem-solving skill. And forces are really good at determining accelerations. Forces don't require you to consider states of the problem. Forces are instantaneous. It's what's happening at the moment. This is the moment we are looking at. So there's differences in the way you approach the problem. Conservation of energy problems require a beginning and an end, right? You are looking at two stages of the problem. But force problems are in the moment. This is at a specific instant in time. So we're freezing it here. Now, I have to make choices in any problem in which there's forces, because forces, unlike energy, have direction. So when I'm dealing with forces or I'm dealing with momentum, I have to choose a direction to call positive. What are you going to choose? What do you think would be best?
Downwards.
I would make downwards positive, yeah. That's the direction it's going to accelerate. I always suggest it to you, if you can, make the direction of the acceleration the positive direction. So I'm going to make downwards the positive direction. Not terrible. Add up all the forces and set them equal to ma. Am I done? Can I solve this for A and walk away? I can't. Right? It has T in it and M in it. So I need more information. I need something else to try and get rid of the T. So I have more. I know it's spinning. I need to create a torque equation. So to create a torque equation, I have to decide on a pivot point. These are all things in your notes, right? You know to do all of these things? Because if you don't, here's where I hit the... I know that torque has more stuff. Like torque requires that I do things. Right? I have to construct a torque. And it requires a pivot point. So you have two choices here, I think. And you'll have to pick which choice you want to follow. I think you could choose either the center of the toilet paper to be your pivot point or the edge of your toilet paper to be your pivot point. I don't care which one you choose, but you have to choose one of them. There's advantages and disadvantages to each. So you tell me, where's the pivot?
At the edge.
At the edge? Then that's what we shall do. We're going to set the pivot point at the edge. It says add up all the torques, set them equal to I alpha. So any force acting on your object could cause a torque. You have to ask if it does. So does the tension cause a torque? Again, in your notes, if you don't know what to do, if you're just stalled, every force could cause a torque. So find out if they do. I picked a pivot point. I wouldn't do this except that I'm looking at people who are just like staring in a blank wall. And so I'm speaking to them right now, not to you if you know what to do. There are two forces. So does the tension cause a torque? And does the weight cause a torque? I don't know. I'm going to see. It's that straightforward. You don't have to know the answer, but you have to move forward. To cause a torque, three things have to happen. There has to be a distance from the force to the pivot point. There has to be a force, and it has to be at an appropriate angle. So, what is the distance from the pivot point to where the tension is applied? I'm looking right here. How far away is the tension from where the pivot point is? I don't think so. I'm pretty sure that they are at the same point, aren't they? The tension's applied there and the pivot point is there. So the distance from the pivot point to the tension is 0. Okay. That was harder than I thought, but okay. So that will be 0 for R times tension times a sign of who cares because I'm multiplying by 0. So now I will look at the other possible tension, or the other possible torque. The distance from the pivot point to where the weight's applied appears to be the radius of the toilet paper. So I'm going to put a big R here for radius. I'm going to put an mg for the force. And it looks like 90 degrees to me, so I'm going to put the sign of 90 degrees. The three parts of a torque. All right, so net torque is the sum of these two. I will add them up and get RMG sine 90 degrees equals I alpha. You need to do something else now. We can't have I in our answer. What shall we do next? Yes? Replace it with the moment of inertia. don't think it's 1/2 mr squared. And here's why. The moment of inertia at the center of mass is 1/2 mr squared. Are we pivoting this thing about its center of mass? No. So we will have to shift the moment of inertia. It's not a big deal, but since somebody said we're doing this on the edge, I'm just following the rules of what they say. I have to follow all of the rules. So I will need the parallel axis theorem. It's not much, but that's what I do next. I parallel equals I center of mass plus how much I'm shifting it. So let's do that. I center of mass is 1/2 mr squared. And looking at my picture, I'm shifting from the center to the edge. How far am I shifting the moment of inertia? 1 radius. So plus mr squared. Now in your notes, what you people need to write down in your notes, because you won't remember, is why did I replace the x with an r? Why? You need to put that in your notes. That's how far I'm shifting from the center of mass to my pivot point. I shifted it from the center a distance r because I'm on the edge. Trust me, that's the kind of little details that you guys ask later. So tell yourself now why I did that. And when I do that, I get 3/2 mr squared. Funny, because I'm seeing a 2/3. Are you seeing a 2/3? I'm seeing it kind of coming into the problem. It's upside down, so perhaps later I will be getting it, but do you see that it's there? That's promising, isn't it? When I had the 4/3 before, it was less promising, but this seems promising. So that's going to be my moment of inertia now. And so I go back down here, r mg sine 90 degrees equals 3/2 mr squared times alpha. All right. Parallel axis theorem effectively done. And now I am I'm getting closer. I mean, things like the sine of 90 I can get rid of. And I can get rid of one of the r's. And it looks like I can get rid of m. I'm getting closer. So let's take a breather here and say g equals 3/2 r times alpha. Close, but not done, right? I got to get rid of the r and the alpha. I want a. So here's where we need more information. Can you think of something that we could use here? Well, I want to get rid of alpha and be left with a. I have to ask myself, can I use this relationship? Can I use it? Is the rate at which it's spinning related to the rate at which it's falling? Yeah. So I can do that. I can plug that in. That seems like a good next step. R's cancel. Solving for a, I didn't even have to substitute. A equals 2/3 g. Looks like I never even needed that. So if I say that there is sufficient friction for this to roll up the ramp, we can agree that this object will slow down on its way up the ramp. We talked about it yesterday, right? Found the height. We did an energy problem related to this yesterday. So what if I asked you guys to go one step further and tell me the size of the frictional force that acts on this object as it rolls up the ramp? We talked about all of the forces acting. Let's say the ramp has a angle of theta. And let's say, pick whether, and I'm actually going to say to you, I want you to do this 2 times. I want you to do it once for a disk and once for a ring, because I think that they are nice and related, and it's nice to know what the answer will be. I want the frictional force. I want you to find the size of a particular force. That's what I want. That does narrow down of your 3 columns which one of your things you should probably use. But I'll tell you, you could probably use more than one. But I'd like the size of the frictional force. This one's not particularly hard or easy. It's the same work, except instead of solving for the acceleration, we are solving for friction, which means in the end, A can't be in your answer. In fact, the only things that should be in your answer or allowed to be in your answer, I think would be those. Oh, maybe theta. Try it. Just see what you start off with. Construct your problem. Use the notes we just took. They will help you. But construct a problem. You could use energy here. I think it's a harder way to go because I want a force. So I think you should probably use forces for this. But just construct the problem.